Am I coming through?
Yes.
Okay, thank you. All right, so today we're going to be doing related rates. We've seen related rates before, but now we're going to do related rates from a trig perspective. But let me review related rates, at least the big idea that we've seen before in the past. Right? Remember, we started related rates a couple months ago, and our first example that we did was a Pythagorean theorem problem, or a ladder problem, where we have to involve Pythagorean theorem. Because Pythagorean theorem relates the three pieces of information that we have. So a squared plus b squared equals c squared, or x squared plus y squared equals z squared. And we always start off with some algebraic or geometric equation, and from there we find the derivative with respect to time. So with related rates, time is the underlying variable that's impacting everything. So as soon as we find the derivative of each variable, we immediately attach a d over dt for that variable. So x squared becomes 2x dx dt, y squared becomes 2y dy dt, and z squared becomes 2z dc dt. Right, and then we gather information from what the problem gives us, and then we solve for the missing variable that's left over in the problem. Similarly, we have problems involving geometric equations, such as volume of a cube or surface area of a cube. And the idea is the same, right? We identify the variables, and then we take time to find the derivative of those variables, and those variables are each going to have a d over dt impacted. So v became dv dt, 4/3 pi stayed as a coefficient, r cubed became 3r squared dr dt. Okay. And then for s became ds dt, 4 pi stayed, r squared became 2r, and the 2 multiplied with the 4 became making it 8 pi r, and then dr dt. So today we're going to see a similar process. We're going to find the derivative, but instead of starting with an algebraic or geometric equation, we're going to be starting off with a trig equation. Okay. All right, so here are the steps. We're going to first list out our known and unknown variables. We're going to write the trig equation that relates the variables. Now, all of our trig related rates problems are all going to be within the right triangle context. So all of our problems, we can just go ahead and draw a right triangle and just try to fill in information based off of what's given to us. We're going to find the derivative with respect to time, just like how we did with previous equations. Now here's something new. We have to create a triangle with trig ratio information, and we'll work through some of these problems and show how this is relevant. From there, we're going to make substitution with our trig from our trig ratio, and then solve for the missing variable. Usually, we're solving for d theta dt with these problems. Rate of change of our angle measure. Okay, so here's example 1. All right, so example 1, a fish is being reeled in at a rate of 1 foot per second from a point 15 feet above water. At what rate is the angle between the line and the water changing when there is a total of 25 feet of line out? So with all these problems, we're always going to have a right triangle to work with. So here's our right triangle. We have 15 feet. This is a constant extending from the top of the water to the top of the fishing pole. There's no information given to us about the horizontal. and then the hypotenuse is the line from the fishing rod to the water, and that's going to create, we know this is going to be changing over time as the fish is being reeled in. We expect this line to be changing, and then at the same time we expect theta to be changing as well, right? The angle between the hypotenuse and the horizontal is going to be increasing over time as well. So let's gather some information from the problem. A fish is being reeled in at a rate of 1 foot per second. So we know it's a rate, but what is this going to refer to? Which variable, what name for that variable can we call that?
Would that be the distance from the fishing pole to the fish horizontally?
Actually, it's going to be this line right here. So the fish is being reeled in, and so it's going to be this line that's changing. Yeah, I think you have the right idea. Yeah, I guess we could think of it as this, but this is what's getting shorter. So this line is the one that's getting shorter. So it's going to be dz over dt, right? So as the line is getting shorter, what adjustment do we have to make? This one is now going to be what? Negative, right? Negative 1 foot per second. Okay, from a point 15 feet above ground, so we have that constant here. At what rate is the angle between the line and the water changing? So that's what we're ultimately looking for. And that's the rate of change of theta, which is d theta dt. Okay, when there's a total of 25 feet of line out, so here's the line. Z is 25. Okay, we do have to be careful here because we don't want to use this information too soon. So we're going to save this until after the derivative. Because if we use this 25 in too soon, then we're saying that this line is never changing, which is not true, right? We know that the fish is being reeled in. This is getting shorter over time, but we are going to use this after the derivative. Okay. Okay, we've gathered some information. Now we're going to create a trig equation that's going to hit all the variables that we see in front of us. So let me draw this triangle, but with just the relevant information that's provided for us. So our decision that we have to make here is choosing between sine, cosine, and tangent. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So which trig equation is going to be the one that's going to hit theta, 15, and z?
Cosine?
Let's see, cosine is adjacent over hypotenuse. So cosine would be this, sine, right? So we want to look at what information is provided for us. So in this case, opposite is given to us, hypotenuse is given to us. So we're forced into the sine equation. Okay. All right, are we good so far? Okay. We have our trig equation. Now we're going to find the derivative. But before we find the derivative, we could go through quotient rule, but I think it's a little bit cleaner if I can move that z to the top and just rely on power rule. Right, since that constant is going to make things easier, I can just bring that z up. Okay, we're going to go ahead and find the derivative. Sine's derivative is cosine. Cosine theta. Now remember, we're dealing with related rates here, so every variable has a time component. So as soon as we find the derivative, we have to attach a d over dt for that variable. Okay, go through power rule here. Bring down the -1, subtract 1 from the exponent. We found the derivative for z, so we need a dz dt. Okay, so this is the one calculus step in our problem. Any questions up to this point? All right, I'm going to do a little bit of cleanup here. I'm going to move that z back down to the denominator. Makes it easier later to make my substitution. All right, let's look at what information we have and maybe what other information we still need to gather. All right, we're looking for d theta dt, so that's ultimately our goal. We have z, right? That 25 is now going to be used. dz dt we have as well, -1. But what's missing is cosine theta. We don't know what to replace cosine theta with. Okay. So this is going to be our new step of the problem. We're going to create a triangle with as much information as we can numerically, and from there we'll make a replacement for that trig function ratio, or that is for the trig function. So let's create a second triangle, but now we're going to fill in with as much numeric value as we can. So we know this 15 is staying constant. We know at this moment in time, z is 25. Okay, so how can I find this missing side of our triangle at this moment in time? Right triangle, so we can use what?
Sine theta is equal to 15 over 25.
But we want to find this missing side though. So imagine you don't see the theta right now.
Pythagoras.
There we go. Yeah. A squared plus b squared equals c squared, right? Pythagorean theorem. Yeah, so we're going to find the missing side, and then we can look to see how this cosine theta can be used. Okay, so a squared plus b squared equals c squared. Use our calculator, we get 20 squared. I'm sorry, 400. Which if we take the square root, x equals 20. Okay. Okay, Pythagorean theorem. We have all three sides accounted for. And now we should be able to find a clean replacement for cosine theta. Okay, what's cosine theta equal to here?
(20/25).
There we go, right? Adjacent over hypotenuse. which reduces to be 4/5. So now we have a clean replacement for everything that we need. Cosine theta as a numeric value. Z can be replaced with 25. dc dt is -1. So all these variables have now been replaced with numeric values, and that will leave us to solve for d theta dt. Okay. Now I want to point out something here. This is where students run into trouble at this point. And I think the issue that a lot of students may experience is they're looking at this problem and trying to figure out what is theta. They have no idea what theta is, and they end up not being able to move forward. But we're not going to just replace theta. We're going to replace the entire trig function. Okay. So when you get to this step, just understand that you want this entire trig function to go away, whether sine theta, cosine theta, tangent theta, secant square theta. We want that whole thing to go away and replace it with a fraction. We don't want to just replace theta, because that's not, it's too much trouble, and we have a much faster way of getting to the answer if we just replace the entire trig function. So when you get to this step here, you're going to look to replace the trig function, okay, and not just theta. Okay, we're not going to replace theta, we're going to replace the entire trig function. I'm going to use the space below for number 2. We're not going to do number 2 here. So let's see here. We should be able to now make our substitution. Cosine theta gets replaced with 4/5. d theta dt is still the variable that we're looking for. -15 over z squared. Z, we have a value for that, 25. And then dc dt is -1. Okay. We want to solve for d theta dt. I'm going to divide both sides by 4/5, which is the same thing as multiplying by the reciprocal. The two negatives cancels out. And then we just make the calculator do the rest of the work for us. And we get 3 over 100. Now, the units of measure for theta is not going to be in degrees. It's always going to be in radians. So we're going to say radians, and then time unit is seconds, so radians per second. All right, any questions with number 1? Okay, let me recap the process. We're always going to start off with the right triangle. Based off of the information that we can gather from the triangle, we're going to have to pick either sine, cosine, or tangent to use. Sometimes with a limited amount of information, you're kind of forced into one trig equation, but other times there may be multiple information, multiple paths to the same answer. So there are times when there's more information that's given, and if that's the case, then you can choose between whether to use sine, cosine, or tangent and still be fine. But sometimes if there's an entire missing side with no information, you're kind of forced into one trig function. But after you find that trig function, you're going to set it up, get it ready for derivative. We go through the derivative process. d theta dt will show up. Another d over dt will show up. We look to see what information we can substitute. We're going to create a second triangle to find a substitution for our trig function. And then it's just a matter of solving for our missing variable by combining the rest of the numbers together. And your units of measure is always going to be radians per time unit. So it could be radians per second, radians per minute, radians per hour, radians per day. But theta is always going to be radians. And the time unit, just whatever the problem is referencing. Okay, we're going to skip number 2 and let's go to number 3. So we recognize this problem, right? A ladder 50 foot long is being pushed against a wall at 5 feet per second. When the bottom of the ladder is 30 feet from the wall, what is the velocity of the top of the ladder? So I'm just going to start off this problem, but we're going to skip A and B. But ultimately, we know it's a Pythagorean theorem problem, so I'm just going to fast forward through A and B here, or sorry, through A. 2x dx dt. We list out all the information that the problem gives us. Dx dt is -5. Dy dt is unknown. And then dc dt is 0. Okay, we plug all this in. We solve for dy dt and we solve for dy dt. I'm skipping all this step here, but it ends up giving us positive 3.75. Okay, so that's all the information from part A. We're just skipping all that. And we're just going to go to part C from here. Okay. Right. Take these 5 variables, plug in, solve for dy dt. Okay. All right, so now let's go to part C here. Part C, at what rate is the angle formed by the ladder and the floor changing? So we're trying to find d theta dt. So here's theta. And now we got to decide which trig function to use. Do we want to use sine? Do we want to use cosine? Do we want to use tangent? But this is the instance where any 3 is going to be suitable because we have more information than we need, and any trig function, we have all the variables accounted for. So we have no missing side with missing information. So you can choose either sine, cosine, or tangent. But I will say, though, that if you can involve a constant, the derivative process will be a little bit easier. Because, for instance, if I try to use tangent will be y over x, and this forces me to have to go through product or quotient rule, because I have 2 variables. But if I can create a situation where there's only 1 variable, either sine or cosine, then my derivative process will just be a little bit cleaner, a little bit easier, because I can just rely on power rule instead of quotient rule. Okay, so I'm going to use sine here, but cosine is fine. Tangent works as well, but we'll pick an easier route here. So if I want to use sine of theta, what's the right side going to look like?
Y over 50.
Yeah. Opposite over hypotenuse. Okay, we listed out our variables, we wrote our trig equation, and now we're going to move to find the derivative. But to make this a little bit cleaner, maybe I can push that 50 out in front. We find the derivative. Sine becomes cosine. And we want to make sure we attach a d over dt. One over 50 coefficient. And then y becomes dy dt. So if we look here, we're trying to solve for d theta dt, right? We're trying to look for the rate of change of the angle measure. Dy dt was from part A that we skipped over. I kind of fast forwarded through that process, but dy dt is 3.75. But we're missing this cosine theta, right? So we're missing that cosine theta. So we're going to go to create a second triangle and see if we can gather that information from the sides of the triangle. So here's my second drawing of my triangle. $50 is my hypotenuse, 30 is my base, and 40 is my height. All right, so based off of this information now, what is cosine of theta equal to?
Thirty over
30
50.
over 50.
Yeah, 30 over 50. I can reduce that, right? 3/5. So now we should be in the clear because now we have a numeric substitution for all these variables, and that gives us a clear path towards finding d theta dt. All right, so cosine theta gets replaced with 3/5. Now I'm going to move over here. Dy dt was from part A, 3.75. All right, so I want to solve for d theta dt. So I want to divide both sides by 3/5, which is the same thing as multiplying by the reciprocal. Which is 5/3. Make the calculator do the work for us here. And we get 0.125 or 1/8. Anytime we're dealing with theta, your units of measure is always radians per time unit, in this case still seconds. All right, Any questions with procedure here? All right, let's look at number 4. All right, a television camera at ground level is filming a liftoff of a space shuttle that's rising vertically. We have a position function, 50t squared, that's going to indicate to us how high the shuttle is off the ground at any moment in time. Find the rate of change of the angle of elevation of the camera at 10 seconds after liftoff. Okay, so I like to just go ahead and create a trig equation here just so we can have some foundation to build off of. This 2000 is going to stay constant. The theta is changing. We know the height is also changing as the shuttle continues to rise. So which trig equation can we start off this process with? Sine, cosine, or tangent?
Tangent.
Yeah. We have opposite, we have adjacent. So that's going to be the best fit, right? Okay, so we'll say tangent of theta is equal to S over 2000. All right. I'm doing things a little bit out of order here. I'm just going to go ahead and find the derivative. To find the derivative, we can then see what variables are involved, and then we can gather the rest of the information after we do that. But I'm going to get this ready for the derivative, push the 2000 out in front so it's not sitting underneath an S. Okay, derivative, tangent becomes secant squared. One over 2000 stays. S becomes ds dt. All right, we'll just find the derivative of tangent, right? So tangent's derivative is secant squared. Both theta and S will produce a time component. Okay, so we're going to pause from this equation for a moment. We're going to gather some information that we need. So based off of this S of t, this is the position function that tells us the height of the shuttle at any moment in time. So what's the moment in time that we're concerned with here?
Ten seconds.
10 seconds, right? So if I plug 10 in for t, I can figure out exactly how high the shuttle is off the ground at the moment in time, right? We're always focused in on a specific moment in time. And we have the derivative already, so we know that everything's already set to go. So I'm going to plug 10 in for my position. 50 times 100 is 5,000. So the shuttle, we're concerned about this moment in time when the shuttle is 5,000 feet off the ground. So we're going to use this later, but if you look, we also need a ds dt. So ds dt is basically the rate of change of position, which is another word, the velocity. So how can I find the velocity at this moment in time? Take the what? if this is my position, what can I do to get to my velocity?
Take the derivative.
Yeah, take the derivative, right? So S can become, you can call it S prime, you can call it V of t, but either way, we go through power rule on the right side, so we get 100t. We're concerned about 10 seconds into, after the shuttle lifts off, 5,000 feet, we want to figure out the velocity, so we can also plug 10 in for t. And the velocity is 1,000 feet per second, which is also ds dt. So S prime, V of t, ds dt, they all represent the same thing. They all tell us the rate of change or the velocity, right? Just different notation, different perspective. Okay. So this required a little bit more work because previous problems just gave this information to us, but this one we're kind of given information indirectly and we had to kind of figure things out, requiring a few more steps. Okay, but now if we look, we're trying to solve for d theta dt, right? That's still our goal here. Find the rate of change of the angle of elevation. We're trying to find d theta dt. So that's still the variable we're looking for. ds dt, we found that the velocity of the space shuttle is 1,000 feet per second, and now we have to build our second triangle to figure out what secant squared theta is, right? So we need to find the substitution for that secant squared theta. So here's my second triangle. Base is 2,000. The height, we found that as well, which is 5,000. And I find the hypotenuse.
Pythagorean theorem.
Yeah. A squared plus B squared equals C squared. And then once we get C squared, we take the square root of that. So it's not going to end up being a very pretty number here, but it's going to clean up nicely. So right now it's going to seem a little ugly. Ends up being 29 million. All right, so now we have all three sides accounted for after building using Pythagorean theorem. So now we need to find what secant of theta is, because we want to replace the entire secant theta with a numeric fractional value. Now, secant is the reciprocal of what?
Sine.
Cosine.
No, it's cosine, yeah. So it's 1 over cosine. So what is going to be the ratio then for secant?
One over. Oh.
Yeah. So instead of adjacent over hypotenuse, it's now going to be what? Hypotenuse over adjacent, right? We're just flipping the order of the cosine. All right, are we okay here? Any questions here? Do we see where these values are coming from? Okay, we should be in the clear now because I know these feel like really ugly numbers, but things will clean up nicely. We're just going to make our substitution. We're going to have to square our fraction for this side. We have ds dt. We'll move it over and we'll solve for d theta dt. DSTT is 1,000, so put that here. I want to solve for d theta dt. I want to move this fraction over to the other side. So I'm going to do two things here. I'm going to make it flip. And I'm also going to square each of the terms. So just to speed up the process here. So I'm multiplying by the reciprocal. So this is the right side is now going to be 2,000 squared up top. In the bottom here, the square root and the square will just nicely cancel each other out. So I'm just left with 29 million. The nice thing about 1,000 over 2,000 can be reduced to be just 1/2. Now we just make the calculator do the rest. It's all the way down to 2 over 29. Units of measure, radians per second. Right. Theta was always going to be radians, not degrees. Okay, always radians. Okay. Any questions here? All right, I got one more for us. This is off of the other handout. This is number 38. If you don't have it, we can just kind of follow along here. All right, angle of elevation. A balloon rises at a rate of 4 meters per second from a point on the ground, 50 meters from the observer. Okay, we're always dealing with the right triangle. Balloon is rising, so I'm going to call this y. We know that's changing over time. The distance from the observer to the where the balloon lifts off is going to be a constant 50. Okay. Find the rate of change of the angle of elevation. We're looking for d theta dt. Balloon is rising at a rate of 4 meters per second, so we know that's going to be a rate of change of y. So we know dy dt is positive 4 meters above ground. That's a moment in time. Y equals 50, and we're trying to solve for d theta dt. All right. So first up, what equation is going to hit all 3 pieces that we need here? Sine, cosine, or tangent?
Tangent.
Tangent.
Yep. Good. We have adjacent and opposite. We have nothing about the hypotenuse, so that forces us into tangent. All right, clean this up. Push that 50 out in front to make it a little bit easier to look at here. All right, we're ready for our derivative. Tangent becomes secant squared. (1/50th) stays. Y becomes dy dt. So we should be making progress here. Dy dt is positive 4. That's a clean substitution. We're looking for d theta dt. And now we want to find a substitution for secant squared theta. So we're going to create a second triangle and see if we can fill in all the sides of the triangle with the numeric value. So this 50 is going to stay constant. We have a moment in time. Y is 50. Pythagorean theorem, a squared plus b squared equals c squared. But you can also recognize this as a 45, 45, 90 triangle, which is 50 root 2 for our hypotenuse. but Pythagorean theorem also works. So now we need to find a replacement for secant theta, right? Based off this triangle, what's secant of theta going to be?
√2/50.
Yeah, secant is the reciprocal of cosine over adjacent, 50√2/50. Which reduces to a nice value of just √2 because the 50 cancels out. So secant of theta is just √2. All right, we should be in the clear now. Everything that we need, we found. So we can solve for d theta dt now. All right. So secant gets replaced with √2, and I'm going to square that. dy dt gets replaced with 4. And now we can just divide the √2 squared over. √2 squared is just 2, so if I divide that over, that just becomes 1/2. We get 4/100, which is 1/25, and that's our d theta dt. Always radians for theta. Time units, still seconds. Make sure you don't put meters or feet or inches, right? With theta, with angle measure, it's always going to be radians. All right, any questions here? Good, so tomorrow we're just going to practice with these types of problems. I have a worksheet available under tomorrow's date. So print that out. It says related rates 10 problems worksheet. So we're just going to spend tomorrow going over that, and hopefully, if you're not comfortable already, hopefully by tomorrow you'll feel comfortable with the process of these types of problems. All right, thanks everyone. Hope you guys have a great day. See you tomorrow.
Thank you.
Have
Have
a
a
good
nice
day.
day.
See you. Bye.
Thank you, Ms. Yang.
See you, Oscar.